Hi, welcome to another lecture within a course on optimal and robust control given at Czech Technical University in Prague. This is a continuation of our introduction into unconstrained optimization. In particular, we are going to extend our first and second order conditions of optimality from the scalar case to the vector case. Recall that what we did in the scalar case was that we considered the critical point that we labeled as x star, and we analyzed how the function behaves in its neighborhood. That means we perturbed x star with some real number alpha. And we analyzed what happened with the value of the function for such perturbed independent variable. So we need to do something like that in the vector case. That means our critical point or stationary point is no longer just a real number, but now is an n tuple of numbers, a vector in n-dimensional Euclidean plane. And now let me first sketch how the situation could look like. So say in the two-dimensional case we could have x1, x2 as the independent variables. This will be the vertical axis, will be the function value, and the function could look like say something like this. Now, in order to attempt at some 3D experience, so perhaps something like this. Now, the point that is suspected of being the minimum, and indeed in this case it will clearly be a minimum, will be here. We'll label it as x star with its corresponding coordinates. And now one idea how to extend this perturbation idea from the scalar setting to the vector setting is that we simply pick some direction and fix it. So let's say we will choose a direction, choose this direction, and now we analyze the function just along this subset in the original plane, just along this line. That means we will analyze this scalar function. Let me now put this formally. So we perturb the critical point with alpha times d, where alpha is again a real number and d is a vector. What's important to emphasize is that d is arbitrary but fixed. So once you choose it, you fix it. So the independent variable here becomes alpha. So similarly as in the scalar case, alpha is the independent variable here. There is an alternative approach that we will mention later in this lecture, and in this approach that I would call perhaps genuine vector approach, we directly perturb our x star with the perturbation vector d, and this time the d vector is is the perturbation itself. So it's both magnitude and direction that are free, that can be used to perturb the original vector. So perhaps sorry. So this could perhaps be viewed as if we were perturbing x in some neighborhood, both magnitude and direction at once. But let's start with the first approach, with the approach of perturbing the original vector along certain line. So what we are doing is that we investigate the behavior of a function along some line. Now, since it's the real parameter or real variable alpha that is varied here, we will relabel this function just for notational convenience. We'll relabel it into g of alpha. And now we are analyzing the behavior of this function around the local optimum, which in this case coincides with alpha equal to 0. So now let's write the Taylor's expansion here, which is the value at the critical point, the point suspected of being the minimum, plus the first derivative, plus the second derivative times alpha squared, plus some higher order terms as usual. And now we can immediately write down the first and second order conditions, right? So for the first order conditions, we can immediately conclude that derivative of g with respect to alpha evaluated at 0 needs to be equal to 0. That's nice, but what we are after is not the g function, but rather the f function. Therefore, we need to translate this result back into the setting with our f function. So what we are after now is the derivative of our f function for fixed x star, fixed d, and alpha as the function, as the variable. So derivative of this with respect to alpha. Now, invoking the chain rule for differentiation of composed functions, we can write this derivative as sum of n terms, and each term is always partial derivative of f with respect to its ith component, with respect to the ith component of the x vector, times derivative of this internal function, of this internal argument with respect to alpha, which is d. So I will have di over here. Now note that this can also be written in a compact way as nabla f, gradient of f, and since in our course we will regard a gradient as a column vector, we now have to transpose it and times d vector. Now, since ultimately what we are interested in is the behavior at alpha equal to 0, so d of f with respect to d alpha evaluated at alpha equal to 0 is equal to gradient of f at x star times d, and gradient needs to be transposed. So let me now write down this, the condition, the first order condition of optimality. Since d can be completely arbitrary, the only way for this product to be 0 is that gradient of f at the given point is equal to 0. So this is our first order necessary condition. For completeness, let me write down that by gradient we indeed understand a column vector, which is always partial of f with respect to x1, partial of f with respect to x2, and so on. I just wanted to make you aware of the fact that here the conventions may vary across the literature. Some people regard gradients as column vectors, some other regard them as row vectors, and yet in some other literature they do not even make this distinction because they do not regard them as either vector or column. They view these just as representations of vectors in a given basis, I mean columns on vectors. But in our in our course we will regard gradients as columns. Now let's go for second order conditions. For that, we need to find the second derivative of g function with respect to alpha, but we can get it as the first derivative of what we already have. That means first derivative of, or let me first finish this. So, pardon. So this can be written as the first derivative of the first derivative. That means we will get this double sum of second partial derivative of f with respect to these mixed terms xi and xj times di dj. Now, if what we are interested in is actually derivative of g, second derivative of g with respect to alpha evaluated at 0, which I very often write using the common abuse of notation as g double prime at 0. So we have again this double sum and second partial derivative of f, but this time evaluated at x star, and again these mixed terms. Now again, similarly as in the first order case, even here we can rewrite this in a more compact format like this. So d transposed times a matrix that I will label as nabla squared of f times times d. So let me now support this by these symbols. Now the matrix that I labeled as nabla squared of F is called Hessian, or also Hess matrix. Sometimes people label it using H. Make sure that you don't interpret the symbol as a really squared or squaring operation. This is rather the symbol for the second derivative. And now, since the second order necessary condition is that the second order derivative is non-negative, this means that this expression needs to be non-negative. And since D, just recall that this is really arbitrary. So we can immediately now ask the question, what can be inferred from the matrix, from the Hessian matrix? What can be inferred about this inequality if D is arbitrary? And it appears that this is actually a standard situation. We have a quadratic function given by or generated by a matrix, the so-called quadratic matrix form, and it is well known that as long as the Hessian matrix, the matrix that generates this quadratic form, is symmetric, which is the case, of course. Let me now write it down explicitly. So the Hessian matrix is symmetric, right? Because let's also put here the explicit expression for Hessian matrix. So it's double or second partial derivative of f with respect to x1, then second mixed partial derivative with respect to x1 and x2, again second mixed partial derivative with respect to x2 and x1, and finally the second partial with respect to x2. So clearly Hessian matrix by definition is a symmetric matrix because these mixed derivative terms must agree. Back to the analysis of non-negativeness of this function. It's well known that for these symmetric generated matrices, the non-negativity condition is satisfied if and only if all the eigenvalues of the Hessian matrix are non-negative, which we write in this notation. So it certainly does not or can't be interpreted as non-negativity of every component here. Whenever we write that matrix is non-negative, what we actually mean is that its eigenvalues, that I will label as lambda, are all non-negative. And finally, so this is first order or second order necessary condition of optimality. And now writing down the second order sufficient condition is as easy as replacing the greater than or equal type of inequality with a strict inequality. So the Hessian of f at x star should be strictly greater than 0, which reads that Hessian is positive definite. Of course, gradient needs to vanish. Alright, so we are done with the analysis along an arbitrary but fixed direction. Now we need to make a transition from the one direction at a time to the all directions simultaneously. So let me write this down. So transition from one direction at a time to all directions. How do we do such transition? Now, recall the very basic trick that we actually explained in the previous lecture. The trick or the fact that allowed us to make some arguments about optimality here. And this argument was that we would always find such epsilon an upper bound on alpha. That means that for all alphas which were smaller in absolute value than this upper bound, we could argue that the second order terms dominated in absolute value higher order terms. So it was only for alphas within this small interval that we could make some arguments. And now in our case, we just in our vector case, we just don't have only a single real axis. We investigated the problem along several directions, right? So let's say if the critical point is over here, so we could then choose a direction like this, and then for this particular direction we could find some particular epsilon. Let's say in this case it will give us this interval. Then for some other direction we could find perhaps some other epsilon, possibly larger, and yet for another direction we could find yet another epsilon. What I want to express is that we will view epsilon as a function of our direction vector. Now, the function can be visualized as a curve possibly looking like this in our particular case. So now what we are after is the following question: can we find among all these epsilons parametrized by D, can we find one that has a minimum value? Because if Now if the answer is yes, this would mean geometrically that we could draw a circle inside this closed curve here, and this would mean that along all directions we could make the argument that we did for just one direction at a time. So all the question boils down to the question of existence of a minimizer for epsilon. Here, by drawing this blue circle or disk, I already answered the question that yes, of course, in this case it can be expected that such minimum exists, but let's now make it a little bit more formal, because this will come in handy in future. There is a theorem, one of the most fundamental theorems in optimization, a theorem by Weierstrass, which tells us that if you have a continuous function on a compact set, then minimum and of course also maximum exists. Now, concerning compactness, this may look somewhat exotic to you, but let's now just mention that for finite dimensional vector spaces, like these n-dimensional Euclidean spaces, this is equivalent to being closed, the set being closed and bounded. Now back to our problem of minimization of epsilon. Obviously, even if I don't give a proof here, it can be accepted, I believe, that epsilon is a continuous function of d. If you change the direction, in this case the direction could be parameterized by the angle here. If you change the direction a little bit, the epsilon, this upper bound on alphas, changes only a little bit. So epsilon is a continuous function, and what is the interval over which we do the optimization? So if we now switch to characterizing the direction using the angle, we could write it like this. So we have a minimization of a continuous function over a closed interval, hence minimum exists. Now this may sound so trivial that you may wonder why on earth we use this complicated analysis. The thing is that whatever looks natural and intuitive in finite dimensional cases may turn out completely counterintuitive in infinite dimensional vector spaces, and that's what will keep us busy in future lectures when we consider optimal control. All right. Now, before we conclude this lecture, I need to give you a warning about how not to interpret the analysis that we presented. Under no circumstances can what I presented here be interpreted in the following way. So, if I can show that my original function when investigated along some fixed but completely arbitrary direction, so if this function along arbitrary direction has minimum, so if it has a minimum when searching along arbitrary direction, then it may be perhaps tempting to think that the original function has a minimum at x. This looks tempting, right? But no, it's not correct. This is not what the analysis that we presented here says. Let me now explain this by means of an example. Let's consider the following function. And now I think at this point I will need some help from some computational tool, because visualizing this will not be that easy. So have a look. This is how the function can look like. You can check it by yourself that the only critical point here is the origin, is the point 0, 0. Now upon its inspection of the function, we can immediately conclude, just from inspecting the graph, that certainly the function does not have a minimum at the point 0, 0. Right? If I pour water on this surface, not even a drop of water will rest at the point 0, 0. And yet, let's have a look at what happens if I analyze the function along arbitrary directions. This can be visualized as if I was making some slices of the function, like this. So perhaps even from this picture you can already see that whichever direction I take, the resulting restricted scalar function of, function of a scalar variable looks as if being minimized at the point x star. You can also have a look directly at the resulting scalar functions. So this is what happens as I'm changing the angle of the direction. So for all angles, the point 0, 0 is certainly a minimizer. And yet the original function is not minimized. So what's the trouble here? Well, the trouble here is that our argument that I gave during this lecture and the previous lecture relied heavily on the fact that there exists this epsilon, an upper bound on alpha, and then that this function is a continuous function of the direction, which is clearly broken in this particular case, because for all directions but one, the second derivative is positive, strictly positive, but for one particular direction, for this particular direction, for pi half, the resulting function loses its second derivative. The second derivative vanishes. So we simply cannot apply the argument that we used for transition from one direction to all directions at once. A comment that I could perhaps give on this is that the deficiency of this line search based analysis is that it always considers rather restricted type of perturbations. Have a look at this contour set, or maybe over here. So we always perturb the function only along some line. Clearly, if we were able to perturb the x vector not along a line but along some curve that would go like this, and visualize the corresponding function, then we would clearly see that the function is not minimized along such curve. All right, so now it's the high time to introduce the other framework that I advertised at the beginning, and that is that so-called, or what I would call, genuine vector approach. And following that approach, we would consider the perturbations directly captured by vector d, so both magnitude and the direction. And the first few terms of the Taylor expansion would then look like this. Now be careful, higher order terms, since the independent variable for us here is d. The higher order terms must be a function of the size of d. So we will have a norm of d over here, and in this case it will be a cubic term. So this gives us also a practical procedure for testing the first and second order conditions. So for first order conditions, have a look at the gradient. That's what we already did. And for second order conditions, just have a look directly at Hessian. Now, invoking back the troublesome example, if we now calculate the Hessian, generally it looks like this. It's a matrix. Of course, here in this computation with Mathematica, I did not use x1 and x2, but x and y, but hopefully you can cope with it. And now if I evaluate this at the origin, the Hessian looks like this. So clearly we can see it's a singular matrix. One of the eigenvalues is positive, one of them is 0. So in order to see what's going on here, we need to investigate higher order terms, exactly as we did in the scalar case in the previous lecture. So in this particular case, if I just calculate the third order derivatives, I can see that there are some non-zero terms here, from which I can immediately conclude that no, the function cannot have a minimum at the point 0, 0. And that's about it. Perhaps we can now summarize what we derived. So, gradient of f needs to be equal 0 at a critical point, and Hessian of f, if it's strictly positive, or positive definite, as we say for matrices, we have local minimum. If it's strictly negative or negative definite, we have local maximum. If it's indefinite, that means some eigenvalues are negative, some are positive, we have a saddle point. And if this matrix is singular, that means some of its eigenvalues are positive, but some are 0. Clearly this means that determinant of the Hessian is equal to 0. Then we have a singular point, and we just can't tell directly from the second derivative, and we need to investigate higher order derivatives. Now that's it, and in the next lecture we are going to practice this for some useful functions, namely quadratic functions.